Okay, today's topic is about methods of extraction of metals from oxides, like how we can separate the metal from their oxides. Again, you should learn the reactivity series, potassium, sodium, calcium, magnesium, aluminium, zinc, iron, lead, copper, mercury, silver, gold, and platinum is there. But we want to extract them from oxide, like we have potassium oxide, sodium oxide, calcium oxide, magnesium oxide, aluminium oxide, zinc, iron. It can be iron 2 or it can be iron 3. Iron 2 will be FeO and iron 3 will be Fe2O3. Lead oxide, PbO, copper oxide, mercury, silver, gold, and platinum. But normally silver oxide is a layer instead of whole compound. We normally have a silver oxide layer instead of the whole compound as a silver oxide. But how we can extract, because how we separate these metal from their oxides, for this you should know the position of a carbon. The position of a carbon, it's between aluminium and zinc in terms of reactivity, and position of hydrogen between lead and copper. So the technique, the method which we use to separate these oxides, separate these metals from their oxide, for highly reactive metals such as potassium oxide, sodium oxide, calcium, magnesium, and aluminum, we separate by electrolysis of molten oxide. So when we pass the current through this molten oxide of aluminum, potassium, sodium, calcium, or magnesium, so we can separate the ions from each other. So we use electrolysis. From zinc till copper, normally the technique which we use by heating with coke, which is carbon, or carbon monoxide. So we can heat these oxides with carbon or carbon monoxide, the metal will be separate. And the least reactive metals, we simply heat them, or by roasting the oxide, simply heating them, remove the oxygen, and we call that as roasting. So example, if you have aluminum oxide and you want to separate aluminum from this aluminum oxide, so what you will do? You will do electrolysis of the molten oxide. How we carry out this electrolysis in detail we'll discuss, but this is just an introduction. So you will take 2 electrodes, and it is molten. When it is molten, it means ions are free to move. The negative and positive ions are free to move. This contain, example, aluminum oxide means it contain aluminum ion and it contain oxygen ion. the plate which is connected with the negative terminal, that's called cathode. And the plate which is connected with a positive terminal, that's called anode. So aluminium are positive ion. Where it will move, towards the anode or cathode? Aluminium ions, the positive ions. Which electrode will attract the aluminium ions? So aluminium are positive ions, so positive ions are attracted towards the negative terminals, cathode. So at cathode we will have aluminium, at anode we will have oxygen. And when aluminium will move there towards the cathode, it will take 3 electrons and change into aluminium metal. So we'll have a shiny solid deposited at cathode, which is aluminium. This is how we separate the aluminium from oxygen by passing a current using electrolysis of a molten oxide, not an aqueous, a molten oxide. Because if you use an aqueous, then hydrogen will move instead of the more reactive metal. Second method, from zinc to copper, which technique we can use? We can heat these oxide with coke or carbon monoxide. This coke and carbon monoxide are also known as, coke means carbon, or carbon monoxide, oxide of carbon. They are known as reducing agent. The term reducing agent means they have capability to remove oxygen, tendency to remove oxygen. That's why we call them as a reducing agents. So what happened, like example, if I was having, say, zinc oxide, if I react with carbon, as we can see, the position of a carbon is more reactive, so carbon will take position of a zinc. So it can form carbon monoxide or carbon dioxide depending on how much carbon is used. Both possibilities are there, and zinc is separated. Or we can also use carbon monoxide. Carbon monoxide is also a good reducing agent. Reducing agent having a tendency to remove oxygen or accept, or they will remove oxygen from other substance or accept oxygen by themselves. So this will become carbon dioxide and zinc. So from zinc to copper, we use this technique, which we call by heating with coke or carbon monoxide, which are reducing agents. And the last one, roasting, here refers to simply heating the metal oxide. Like example, mercury oxide is there. We supply heat energy. So the reaction will be endothermic. It will form mercury metal and oxygen. So the equation is balanced now. So what we call this process as roasting. So these are the techniques which can be used to separate the metals from their oxides. Look, electrolysis can be done for all, but why we are not doing this for every, like we can remove any kind of metal from its oxide by doing electrolysis, but why we don't carry out for zinc, iron, lead, copper and mercury? The reason is that because electrolysis increases the cost of extraction, because you have to pass the current, so you have to generate electricity, so that increase the cost of removing the oxygen from the metal, or cost of a reduction. That's why we don't use electrolysis for all of them. So electrolysis can work for all of them, but we don't use for others. Why? Because it increases the cost. In detail, the extraction, what you will learn extraction in detail for aluminium, for zinc, for iron, and lead. These are the extraction you have to learn in detail. Any doubt in this part? The above metal oxide, because they are stable to heat. You cannot simply roast them. Like if you have potassium oxide is solid. So when you supply the heat energy, you can melt potassium oxide. It will convert into molten potassium oxide, but still the compound remain potassium oxide. So roasting cannot be done for more reactive metal. Only the bottom, the least reactive metal, roasting can be done, but more reactive metal, roasting cannot be done. Electrolysis can be done for all, because when you pass the current through the molten oxides, the metal and oxygen are separated from each other. In your course, you will learn in detail about extraction of aluminium, zinc, iron, and lead. Take the screenshot of this, then we'll move on to the next topic, which is extraction of aluminium. Extraction of aluminium, first thing, you should know how aluminium exists. You don't find like free aluminium, you don't find aluminium metal as alone, because it is a reactive metal. So it tend to react with other substances. So how we find this aluminium? We find this aluminium as aluminium oxide, which contain impurity iron oxide. Iron 3 or iron 2 oxide. And this compound, how we naturally find the elements like compounds, naturally occurring compound, these are known as ores. The term ore means it is a naturally occurring compound of metals. So how aluminium exists? Aluminium exists as aluminium oxide, and it also contains impurity, which is iron oxide. And this aluminium oxide, which contain impurity iron oxide, this ore is known as bauxite. So you have to learn this name. So bauxite is the ore of aluminium, like how we get aluminium. Aluminium is extracted, but you don't find free aluminium, you find aluminium oxide, plus it also contains iron oxide. So first thing, because as we discussed, we can separate the metal from oxide, like aluminium. Which technique we use? We use electrolysis. But the problem here, that aluminium is not a pure aluminium, it also contains impurity, which is iron oxide. So first thing, we have to remove the impurity iron oxide. So how we remove the impurity iron oxide? For this purpose, we add sodium hydroxide. So for this purpose, we add sodium hydroxide. When we add sodium hydroxide, this contain aluminum oxide, and iron oxide. Aluminium oxide, the nature of aluminium oxide is amphoteric. As we discussed the type of oxides. And what's the nature of iron oxide? Iron oxide is a basic oxide. So if I'm adding sodium hydroxide, I add NaOH. Which one will react? As we know, basic oxide can react with acid, but no reaction with base. I'm adding sodium hydroxide or alkali or a base. Which oxide will react? So the amphoteric or aluminum oxide will react, but iron oxide will not react. Yeah, that's right. Aluminum oxide will react because it is amphoteric. Amphoteric means it can react with both acid and alkali. So aluminum oxide will react with sodium hydroxide, form sodium aluminate. That's a compound which is a complex compound. A complex compound means which contain two or more different types of metals. So it forms sodium aluminate, which dissolve, and iron oxide will not react with sodium hydroxide, remain insoluble. So iron oxide will not react with sodium hydroxide and it will remain insoluble. So one substance dissolve, another substance insoluble. So how I can separate them now? If one of them is soluble and the other one is insoluble, how I can separate? So we can use a filtration. So when we use filtration, the sodium aluminate pass through the filter paper known as filtrate, and iron oxide left on the filter paper as residue. So iron oxide left on the filter paper as a residue, where sodium aluminate which passes through. Sodium aluminate which passes through the filter paper, and iron oxide left on the filter paper as. Yes, you can just mention filtration. I'm just pointing out what will happen. You can just mention use filtration, because I'm discussing in detail. So I'm pointing all the points which you should mention. This is step one. But now what we have, this iron oxide is separated, but we don't have, because we discussed extraction of aluminum from oxide. So we don't have oxide, we have sodium aluminate. The sodium aluminate is there. So now we have to convert this sodium aluminate to sodium oxide. So how we will do this? Take the screenshot, then I'll move on to the next part. Then step 2 is converting sodium aluminate to sodium aluminate to aluminium oxide. So how it is done? Basically, this is done by thermal decomposition. Thermal decomposition means we'll supply heat energy. So when we supply heat energy, this sodium aluminate because sodium aluminate is a formed by a reaction between aluminum oxide and sodium hydroxide. So when we supply heat energy to sodium aluminate, it decomposes back to the reactant. What were the reactant? It will form aluminum oxide plus sodium hydroxide. So basically we decompose a compound. You can see initially how this compound is formed. When aluminum oxide was reacting with sodium hydroxide, it formed sodium aluminate. And iron oxide does not react, so it remains insoluble, and we separate them. Then this compound is not too much stable. So when we supply heat energy to this compound, it decomposes and form aluminum oxide and sodium hydroxide. And this aluminum oxide what we call this aluminum oxide is known as alumina. Then there is a method to separate this aluminum oxide and sodium hydroxide, but you're not going in detail of that. So aluminum oxide is formed, and this aluminum oxide is known as alumina. Yes, what's the question? How sodium hydroxide? Why not sodium? Only because of hydroxide turned into water in the last reaction. Now, in the last reaction, when you see, you was having sodium hydroxide, NaOH reacting with aluminum oxide. So when NaOH is reacting with aluminum oxide, it was forming sodium aluminate. So sodium aluminate decomposed to form back the same substance, aluminum oxide and sodium hydroxide. And this alumina, is it clear? You can use mic if you have any doubt or a question. Because maybe writing or typing a question take time, so you can use the mic. So now this is alumina is there. Now we have alumina. What we will do? This alumina, we will do electrolysis. Alumina means aluminum oxide, pure aluminum oxide is called alumina. When we have pure aluminum oxide, we also call that as alumina. Then step 3 is electrolysis. So what we will do electrolysis. For this electrolysis, this is the electrolytic cell which we use. Anode and cathode both are made up of the positive terminal. So the part which is connected with the positive terminal is called anode. So these are the rods of anode. And the part which is connected with the negative terminal is known as cathode. So basically the walls and the base of this container is a cathode. And both are made up of graphite. Anode is made up of graphite. This anode and cathode, they consist of carbon or graphite. Graphite, why graphite? Because it's unreactive inert. That's why we prefer graphite. Now what we do electrolysis of aluminum oxide. So when we do electrolysis of molten aluminum oxide, so what are the ions present here? Aluminum is there and oxygen. So to melt this, because we need a molten aluminum oxide. Molten means we need in a melted state. So if we want to melt this, we need about 1900 degrees centigrade approximately. So we have to maintain this much high temperature to melt this aluminum. When the aluminum is melted, aluminum ions, now because in a molten state, aluminum ions can move towards cathode, so they will move towards the base or the wall, and oxygen ion will move towards anode. So if I write what will happen at anode or at cathode, the negative terminal, what happens? That aluminum ion is attracted, its charge is +3, so it will take 3 electron and it will change into aluminum metal. So we'll have aluminum deposited at the base or the walls. And what about at anode? What will happen at anode? At anode, oxygen, which is -2, will lose 2 electron, but if 2 oxygen, they will lose 4 electron and form oxygen gas. So we'll observe oxygen gas is released. But sometime what happened, because the temperature is too high, because of high temperature, oxygen formed at anode react with carbon of anode, form carbon dioxide. So anode size reduce or decreases. So it's not like direct reaction, but oxygen which is formed reacted with a carbon because it's a graphite. Look, for oxygen, one oxygen is -2, okay? So one oxygen is -2, it will lose 2 electrons and change into oxygen atom. But oxygen is a non-metal. Non-metal cannot exist as an atomic state, only except group 8. All other non-metals as diatomic. So when 2 oxygen ions will reach there, they will lose 4 electrons and it will form oxygen gas. That's why it is O2. This is for one, but normally because oxygen does not exist as atom, it's a molecule, so it will be O2. Is it clear, this extraction of aluminium? So we have to replace this anode time to time. The size decreases, so it must be replaced. Any doubt in this part, extraction of aluminium? We need this method to extract the aluminum, to separate the aluminum metal. For endothermic reaction, yes, you can just make a triangle, which also shows that energy is being absorbed. But there is a problem with this process. What's the problem? The temperature is so high, 1900 degrees centigrade. So the temperature to extract aluminum is so high. What we should do? Yes, you can take the screenshot. So the temperature is too high for the reaction. So to overcome this, what we do? We add cryolite. Another compound. What is cryolite? Cryolite is NaAl3F6. That's the formula for cryolite. NaAl3F6. What is the advantage of adding cryolite? Number one, because whenever you add impurity, what impurity will do? Cryolite is impurity. So when we add impurity, it will lower the melting point, because impure substances have low melting point than pure substances. So it lowered the melting point and reduced to about 980 degrees centigrade. So you can see, if without cryolite, you have to melt, you have to supply enough energy so that the temperature is 1900. But with cryolite, you can melt this aluminum oxide at a low temperature. Second thing, it increase amount of aluminum, because cryolite also contain aluminum. And the third thing, it increase the conduction because it contain more ions. So it increases the conduction. So aluminum oxide dissolve in cryolite before electrolysis, or mix with cryolite before we carry out electrolysis. Yeah, it's Na3AlF6. Then the total charge will be same. Not the formula for cryolite, I think I'm missed here. It's because whole should be balanced. Sodium is +1, so 3 will be +3. Aluminium and F6. No, we are not melting a substance that add cryolite. We add cryolite and the mixture is there of aluminum oxide and cryolite, and then we supply heat energy and melt it. So it can melt about 980 degrees centigrade, which is an advantage. It reduces the cost. Is it clear, this process? So first we started with aluminum oxide, which consists of impurity, iron oxide, and the ore is called bauxite. Then we mix this aluminum with sodium hydroxide. Then we filter and heat it, then carry out electrolysis. Then instead of carrying out electrolysis of the molten oxide directly, we carry out electrolysis of molten oxide with cryolite, so that it lower the melting point, concentrate the ore. The meaning aluminum oxide, like aluminum oxide mix, the meaning of this sentence, like before doing this electrolysis, like this part, aluminum oxide is mixed with cryolite or dissolved in cryolite. Like both are mixed together and then we carry out electrolysis. Is it clear now? The extraction of
Sir, I have
aluminum.
a question.
Yes, Mohsen.
Sir, for sorry, cryolite.
Yes, cryolite.
It's molten, or like its nature. We dissolve aluminum oxide in it.
Actually, it is dissolving aluminum oxide in it.
Yes, sir. What's its state?
The state is, no, initially it is solid, but when we use the term it dissolve aluminum oxide, what we mean that we contain more cryolite and less aluminum oxide is there. Like you have two solids are together, okay, mixed together, and you are supplying heat energy. When you supply heat energy, cryolite and aluminum oxide mix with each other, and now the melting point, like the molten state of the two solid, occur at 980 degrees centigrade. Instead, if it was pure, you have to reach a temperature about 1900 degrees centigrade.
Oh yeah, okay, sir.